What I'd like to do to start off here is to actually ask the people who were speakers who are online to address these questions, and that may just be enough to start the discussion off. And I'll have Brendan, my co-chair, Brandon Schmidt, take notes during the process, and I'll kind of lead the discussion. Feel free to jump in anytime. This is a very informal session. So let's start by asking, how about who's online right now? Who's actually online with us? Before we start, I'd like to point out that in terms of what NASA is supporting, just to keep this kind of in the back of your mind, the Space Technology Mission Directorate roadmaps are out, and one of the ones that's particularly relevant to the things we'll talk about today is power and energy storage, and it might be worth taking a look at, but there is some discussion of the needs for these systems that support more efficient operation, energy storage, and power. And generally, they're made for larger systems. There's not much discussion in the roadmap itself about smaller systems. So that's something, the compactness part, that we need to keep in mind in terms of the things we need to do. So, okay. So let's start with, Shastikant Manakonda. He's been in the room to address these questions and stimulate some discussion on the questions we have for the design challenges.
So, the issue at hand is the energy storage systems. As I understand, that's one of the key challenges, is to address how we are going to provide the storage. The solution that I discussed about, which is just at a very conceptual level at this point, is using superconductors, HTS superconductor cable for storing the energy. It's probably in the modest level. I wish I had the number there. I think it's in terms of a megajoules that you can store, and those would be powered through a solar energy. So that's one solution that we see can be deployed in space as well as on the surface of a planet. But as I am just becoming aware that we also have a need to have these energy storage at a smaller scale, and I am actually just, as we speak, I'm thinking about how if we can address this solution, using superconductors in a way. Maybe there are already a lot of SMES systems existing based on niobium-3 or any other type of more conventional superconductors. Maybe a compact form of those could be adapted for the purpose.
How malleable are they in terms of stowing and shape, basically shaping to fit your environment, to fit your need? How much can they be modified in terms of change of shape and stowability?
The conventional ones, we don't have a lot of scope. Small, unless we make it as a part of a design parameter, typically we have a very small temperature margin that we give because we want to maximize the current density there. So unless we design them with extremely large current margin and the temperature margin, we can then have a bit more shape changes, and we can accommodate the localized energy production that happens there and spread the heat around. But that's something that has to be looked at and see whether we can still beat the traditional systems when we have such a system like that.
And if you're talking about, can you have a multifunctional system? I mean, can you combine energy storage and magnetic shielding in the same system?
Energy storage and probably. I mean, the thing is, like energy storage and for instance, the active shielding. The problem is, yes, the active shielding can store the energy, but that can only be used while it's in the orbit. You cannot bring it down. So you really have to have a separate system that you would want to bring it down and deploy there locally and then charge it.
Okay, so there's the energy storage concept you were talking about was for things that are essentially in space.
Yes.
So they're in orbit or they're in deep space between point A and point B, somewhere in deep space.
Or they could also be deployed on the surface of the planet, and then you charge them slowly, slow charging them over a certain period of time, and then you can store the energy, and then you can deliver it in an efficient way to whatever means that you need.
And how would you extend that to make it work, for example, if you were looking at a protection of something on the surface of the moon, a large facility, let's say, not having to scale it down, but or on Mars to protect from a lot of the secondaries? How would you?
Yeah, I mean, same thing. I mean, the thing is the materials have to be somehow brought in there. I mean, so we need this if we are going to use that concept, or if you are on the surface of the planet. I mean, you could use the materials to provide. I mean, you just have the materials available. So passive shielding is probably enough to build a structure which is dense enough to protect you from the shielding.
Yeah, I personally like the idea of just using existing structures, if at all possible, to provide most of the shielding rather than having to import a lot of materials.
That's right. For the shielding itself, I guess on the surface of a planet or a moon, we could probably use the existing material over there.
Mm-hmm.
But for the energy storage, we may have to bring in materials from outside.
John Fotenauer is asking a question online. Okay.
There we go. Good morning.
Morning.
I wasn't a question so much as just a comment that in agreement that the HTS coil is, I think, just an excellent idea for storing energy on the moon, because it loves to be sitting at the colder temperatures, and as the previous speaker mentioned, you would definitely want to do some kind of an optimization to minimize the mass of what you had to bring up to the moon for that HTS coil. Typically nowadays, I think as many people know, though, for energy storage, HTS materials are typically wound in a pancake shape. So you could imagine bringing a number of pancakes up that are fairly compact. You'd have to have some assembly of those pancakes to make your full energy storage, but it might be modular in that case, that you could define how much energy you wanted to store based on how many pancakes you coupled together.
One limitation that we have currently, I mean, which probably would be solved in near future, is if we are taking a small pieces sections at a time, we need to splice them together. There is the splicing of the superconductors is not a trivial issue, and at this point, I guess you could get the resistance down to close to 10 to the power minus 12 ohm or so. I mean, that's what we are hoping for in a splice joint. Ideally, a superconductor would have some resistance which is probably 10 to the power minus 18 ohm or so. So if we can get a splice joints which are in that order, that would still generate a watt per splice joint. So it's a consideration that has to be kept, that when we are implementing such a solution, we need to also worry about how many small sections we are going to make, and how many splice joints we have to create.
That is precisely, I guess, why I made the comment during my presentation this morning too, that you're likely to have some heating in these HTS coils, and being able to manage that effectively is certainly a design issue you have to pay attention to.
Well, where do you think this technology is going to be going in the next 5 or 10 years in the way of more efficiency in terms of providing for the amount of mass that you expend or the amount of volume, either a power storage capability or shielding?
Yeah, I mean, at this point, the whole thing is the development of the HTS superconductors, how they are driven. I mean, they are at this point driven by some large projects like ITER or some other accelerator projects which are driving the development there. But I guess if the involvement of NASA in this kind of development, I mean, which NASA is involved, but if there is a big project that comes this way, then cables optimized for these applications would be developed.
So in other words, if suddenly there was a great deal of interest in a big venture like sending a human crew to Mars, for example,
Right.
how much would it take? How long and how much investment would it take to make magnetic shielding for a human crew of maybe, let's say, 6 people who'd go to Mars using a thermonuclear engine, let's say months instead of years? How much, how close are we to being able to do that? If the investment were available, and how much investment are we talking about? Any idea?
I cannot put the numbers as such, but in terms of the time frame, as I mentioned, there are in various issues like the current density that we need to achieve. We are around 50% of what we currently are. So,
Okay.
and when we talk to the superconductor manufacturers, they point out that they can have much higher current density.
I might mention that there
Need to
are
have a
some
project.
projects as well.
Work on.
In other words,
So, go ahead, please.
John?
Yeah, I was going to mention that there are some other projects for example, that the Navy is carrying out where they're also interested in trying to keep things compact that you could leverage as far as development of coils, and maybe not the magnetic shielding idea, but certainly the energy storage idea would carry over.
And I'm sorry, we missed the first part of that sentence. Could you repeat the first part of that thought?
Sure, I'm just mentioning that there are other programs that are actively pursuing energy storage with HTS materials. For example, the U.S. Navy has a program at the moment doing that.
And the large power generating companies.
Large power generating companies also have.
Right.
And these projects that are going on, they're actually utilizing systems, or they're what, in use now, or how close are we to actual utilization of these systems? Are they now operational?
Yes, the power in the power industry they are operational. A lot of test facilities are there which are using for efficient power transport. But these are at the level of several meters, not in kilometers, as we would need eventually.
Okay, several meters, and the present ones, so we're not talking about, they're relatively small, in other words, not big enough
the
for
scale
space.
of the cable that we are looking at is a bit smaller at this point, but that has to be the production has to be scaled up. And
But it sounds like it's scalable upwards.
yes,
It's the other direction, scalable downwards, that's potentially more problematic than scalable upwards.
yeah. In that respect, in fact, I had the question of what is, when we say scaling down, what is the amount of stored energy that we are talking about?
Well, let's talk about systems that could deliver something like on the order of maybe 10, 15, 20 watts.
And over over how much duration this has to last?
Okay, so let's say we're talking about the worst case scenario, which is essentially lunar night. And in order to provide enough operation to have at least a skeleton crew of instruments operating, you're talking about something that needs 10 to 15 watts to operate for 14 days. Or, you could find one of these more or less permanently shadowed areas, I suppose, and if you could provide enough storage, of course you have to store energy from somewhere. With power beaming, as David suggests from time to time, you could store that beamed power and then operate for longer. But even just talking about a conventional lunar night, 2 weeks, maybe 10 to 15 watts of storage. And it gets pretty cold, but probably not, let's see, it gets down to, probably about the upper limit of the HTS operational range, probably in a lot of places on the moon during lunar night. That seemed like something that would be ultimately doable.
Right. What's the surface temperature at during the lunar night?
100K.
100K.
So let's say between 80 and 100K.
Yeah, when we looked at this before,
Yeah.
So there's 2 basic ways you can do it with superconductors. One is a flywheel, mechanical flywheel. The other is the magnetic systems. And that the advantage of their magnetic systems is actually the fact that you can make large systems. And like once you're at the moon, you can inflate stuff, and it doesn't really matter how big it gets. So that could be one real advantage of their technology. Is that you could get it there and then inflate it to be a large, which gives you more energy because it's the energy density that's a problem. If you want energy density, then the flywheel model becomes better And we didn't get the full calculation, but I think Wei Kan was saying that he believed that not a CubeSat size flywheel, but maybe something the size of this table could provide a lunar night's worth of a couple kilowatt hours.
What about flywheel technology for a lunar rover? I know that sounds crazy, but
Yeah, no. Well, we looked at it. In fact, Abraham and I did a little bit of work on it, and then we were going to work with Wei Kan to get some more numbers, and then his health didn't really allow. But that's and so now we may set it up as a challenge of can you build a modular CubeSat program where you've got CubeSat-sized flywheels, and each one has like a tenth of a kilowatt hour, and then you can gang them together. And then basically what ends up happening is they're good for temporary storage. So that's the idea. Is you can get the duty cycle down, where you can charge them up and then run for a couple hours.
and then you can recycle. Can you have a large number of cycles?
Yeah. That's with both of these, the cycle is more or less infinite.
Okay.
And then the other piece that comes into it is you'd want to do some shielding and try and keep the temperatures down around 40 and 50 Kelvin, I mean thermal shielding and radiation, because the efficiencies at 40 Kelvin are, what is it, double, triple?
Right.
Well, if you're in the right place, you can get 40 Kelvin. If you're in these areas near the poles that are shadowed most of the time, in some places. Well, this is true. If you want to, and then, of course, if you go down a meter on the moon, you have a probably more or less constant temperature. That's some average of the extremes, approximately.
Yeah, what you'd end up doing is setting up your own sunshades.
Yeah.
And so you wouldn't dig down very much because once the soil temperature gets well above 100 K very quickly. But what you could do is you either build a little trench, because that's one of the nice things you could build. If you were laying cable, you could just put it in a little tray that's probably a few centimeters high at the poles, and that blocks out most of the sun, and now it would stay nice and cool in the middle. And so there's some, and for like insulator, you could use the soil, because the soil is a very good insulator.
Yeah.
If it's already cold, right? But it's once you dig down, it's no longer cold because it's such a good insulator. It's warm very quickly.
Yeah.
So there's in some cases you can use the local materials, in other cases it's harder. But there's a lot of varieties, and so it becomes which is why the original name of this workshop was Lunar Superconductor Applications, because there are a lot of opportunities to find these native solutions, and some of the things that are easy are like laying long cables if you can make long cables, and then creating a sun-shaded area, because that's in order to get down to 40 Kelvin, you need kind of double shaded, permanently shadowed craters. So you bring along your own sunshade. But so there's some serious opportunities, but as we have discovered, is most people aren't working on small solutions. But the real big innovation from AML, your technology, is that inflatable design. Those flexible cables was a huge breakthrough when it was first done. And so just that opens up a variety of potential applications, and right now that's the other, waiting for some particular application, just like Mohammed. Somebody's got to need one before they can build it.
Let's have Mohammed respond to these questions and bring in the technologies that actually exist now, and could this actual funding develop at least at some low level for a lot of different applications. So Mohammed, would you like to take a shot at these 3 questions that we're asking as part of the design challenge? Maybe we can ask John, actually, to talk about heat pipe technology and look at these 3 different questions in the design challenge while we wait for Mohammed to get connected up again. John, are you online?
Yep, I'm here. Can you hear me all right? Yep.
Great.
Yeah,
we can hear you.
Okay, great. As far as the design challenges or for the pulsating heat pipe technology, there are a couple of key issues that need to be addressed. We, of course, described the fact that you've got the evaporator and the condenser ends, and then there's this adiabatic region in between the 2 ends. And so far to date, all of the experiments that have been done have had a relatively short adiabatic section. on the order of 10 centimeters. And people don't know yet how well the same devices will work if that adiabatic section is much longer, which of course would be interesting if you're trying to transfer heat over significant distances. So that issue is one that's out there. I think also how many turns you would need to transfer a given amount of heat has been suggested by some of the correlations I showed, but I think it needs to be confirmed and orientation dependence. So there are a variety of issues that we have a first cut on, but need to be confirmed.
What about a variety of operating fluids that could operate in different temperature regimes using this technology?
Well, you're limited by the difference between the triple point and the critical point for whichever fluid you choose, and of course with pure fluids we know those pretty well. So as I mentioned, if you're going to combine this technology with a superconductor, a high temperature superconductor, then the options are pretty minimal. You're looking at oxygen or neon or hydrogen, depending on how low in temperature you can go. If, on the other hand, you wanted to use the same technology as you were suggesting to transfer heat into some region, you're in a completely different temperature range, and I think there are wider variety of fluids as you go up in temperature that you could use.
So the standard avionics range, even extending it down with colder temperature electronics, I mean, we're still, we're probably talking about something that's a lot higher than high temperature superconductor range. So let's say if we were talking about with existing battery technology, which is the toughest component, somewhere between 30 degrees centigrade and let's say minus 80 degrees centigrade for operating. It seemed to you that we could find a simple fluid or a mixture of fluids that could meet our needs for doing heat transfer.
Yeah, not a problem. There's a myriad of fluids that have been investigated already up in that temperature range.
And is this the kind of thing that could potentially be useful in a package that was going to be subjected to long periods of operation without any power source?
Yes. I mean, in the sense that it's completely passive, it'll sit there as long as you need it to sit there.
Actually, a lot of long periods when it's actually relatively, well, I guess cold really depends on the fluid that you're using. So
there's that, but it also, looking at the design, since you have the air gaps, the expansion of the fluid, if you froze or heated it, probably would store in a much colder temperature just fine.
Yeah.
That was my question. How flexible can the tubes be? Can you, even like in the 10 centimeter runs, can you bend them? And
yeah. At the present time, what we've been investigating were capillary-sized tubes that were either stainless steel or copper nickel. At the sizes we've been using, they're fairly flexible, and the bend radius is down to on the order of a centimeter or so. At higher temperatures, that's an interesting question. There may be other materials that would be more flexible that you could imagine investigating. The one thing you'd have to keep in mind, I think, is that typically the fluid, because you are operating in the range between the triple point and the critical point, could have a higher pressure, so you want to make sure that your tube can handle the pressure limitations. But for small tubes, that's also not really a serious problem.
yeah. So on the number of coils, how does that scale? Is it better to have lots of coils? So if you could have thousands, would that be better than tens?
Yeah, I mean, the correlation that I showed before had just the overall heat carrying capacity scaling like I think n to the 0.75 power. So so it isn't linear with the number of turns, but almost.
Good.
So if we were operating instrument package and we were generating, let's say, watts in an extremely cold environment, the heat that would be generated by actually turning the instruments on could be enough to drive a heat pipe that could keep the batteries warm.
Yeah.
Is that a false or a true statement?
I think that's true. That's a very effective use of your heat that you're generating. You could transfer it readily over to the batteries with a pulsating heat pipe.
Cool.
Yeah, it seems to me this would be a very profitable thing, because in spacecraft, and especially the kind of small spacecraft we're thinking of, just shunting heat a few centimeters would make a big difference. The other thing that, from the systems I've looked at, once you get down to 40 Kelvin or so, being able to jump the heat up from a well at 40 Kelvin to one at 80 Kelvin changes the type of cooling systems you can use. So anything you can use to kind of shift the energy to higher temperature domains gives you now more technology to then dump the energy. So there's that's another thing, is what you're really doing is not necessarily getting it all the way out to space. It's getting it from, you know, a modest shift, and then you change to another heat control system.
Yeah, and you just have to keep in mind what the limits of your fluid physical parameters are. So if you had an oxygen one, you wouldn't want to go below 55 Kelvin, and you'd have solid oxygen. But you could imagine doing a couple of pipes, maybe neon, to go from 24 up to 44, and the 44 to 55 gap is still there. But
another question in terms of potential applications. You know, the commercial goal is to mine frozen volatiles, and the LCROSS mission showed that there's an array of volatiles there, most probably cometary in origin, but you know, there might have been in the past volcanic venting. The solar wind certainly produces deposits of ice as well. And so we don't really know, except from one location, how much of that is available and the mining of it. But it seems, based on, you know, one point that's been measured, that there are a variety of different cryogens. And so if we're going to use those gases, then they have to be heated and separated. But then, in order to be stored, they have to be cooled down again. So this seems an obvious application. That scaling the heat pipe technology is something that's significant, and also locating these facilities close to the edge of where your permanently shadowed region is, where you're doing the mining, and close to a sunlit region where you have the solar energy supplies. You know, there's some being able to position this without having long lines. It seems that we're space critical here. So it seems to me that one of the demonstrator objectives would be to look at some breadboard scale things that we can send to the moon and demonstrate that we can do this on a relatively small scale, and that's a precursor investment to looking at industrial fuel production and industrial mining. So, you know, being able to do this on a small scale, I think, is also relevant to the more obvious large applications. But I think that's something we can keep in mind as an area for some challenges and some further workshop consideration.
Yeah, and there's really, I mean, it's important to make the distinction between that. We've talked about a range of applications here. And we've talked about small packages that are essentially going to be put in a place that's most valid, regardless of where that is, and having to deal with the different regimes that would mean, to deep space applications that could involve protection of large systems, to surface applications at the poles that could involve human crews or on Mars, and then to actual looking at for resources in situ where you might want to take advantage of being next to a place that was nominally 24, you know, always illuminated, but there's no such, according to Ben Bussey, remember, there is no such thing as either all illuminated or all dark on the moon, but, you know, with maybe you have to take into consideration maybe at the 70 or 80% level for, you know, two places juxtaposed that are almost always illuminated and almost always dark. I know there were a couple people that have questions, so Abraham, did you have a question, or was it Tom? Okay.
Tom Riley, Big Moon Dig. All right, it's not that any point when you're getting down in those permanently shadowed is, the permanently shadowed means it's permanently shadowed. But if I put my photocells on a post and stick it up a couple of meters in the air, there are plenty of areas where the angles of the sun is so low that you can be in permanently slated with your photocell
There.
in the sun only a few meters above you.
It's possible, yeah, that's right, it is possible,
and-
depending on where you are. If you're high enough up and you're above the surroundings
Yeah,
enough.
At these
and you're
low
near
sun
the-
angles, it don't have to be very high, but then you have this enormous time scale of, oh, this patch has 12 minutes over here, and this patch has an hour over here, and this patch, you know, and you're running around playing Chase the Sunshine, which is quite doable.
You do have to design a system. Part of your system has to survive in the local environment. You do have a power source to contend with, but you'll still have to make a system that can deal with that.
The low end of it, the problem is any heat from your electronics is boiling your sample away while you're trying to collect it.
Well, if you don't design your mechanism properly, that's right. Yeah. That might be something worth talking about a little bit. The technologies for sample collection. Anybody in the room like to weigh in on that one? Because you guys that are working on Resolve have thought about that a little bit. Would you like to say a few words about that? How to do sample collection if you're talking, or just sampling very cold samples in terms of dealing with volatiles? I know you guys have been thinking about that. Catherine or Ariel?
Hi, this is Kate. I don't know how much we personally can speak to this. We know that there have been trades we have a sample acquisition and transfer system that is going to be responsible for drilling down into the soil. We'll go about a meter down. And I know that there have been trades looking at how much volatiles will boil off before we're able to transfer into the oven. But the current designs that are being looked at are, I guess have accepted the losses or that will take place before we're able to transfer it over to our furnace to heat those up. Ariel, do you want to expand on any of that? I know I'm not able to provide too many details.
I guess I'd like to, this is Ariel from NASA. I guess I'd like to say we could talk a lot more about this in the PM session today.
Yes.
We've got a lot of slides that talk about everything. There's so many trades that we're looking at on exactly how to do this. This is one of the big ones, yes.
So
Yes,
that's
I
a
think
good reason for everybody who's listening in during the morning session to join us again this afternoon.
Go ahead, Tom.
One quick point. From a commercial standpoint, the volatile you want most is helium-3, and it has to be the leakiest damn stuff in the universe, and therefore the hardest to actually deal with, and it's still gaseous at these temperatures. So you're having to deal with driving it off of surface concentrations on the crystal, and we just don't, on crystalline structures, and we just don't know how well we can do it, but it's the only one worth shipping home.
Well, I've often thought that what you'd really like to do is provide a sort of locally heat up a surface and have a collection mechanism that would mean you have a relatively high capture rate per portion of the surface. And actually, that particular strategy is sort of used for doing mass spec. So you have little tiny nozzles, but something that can both volatilize material and collect it, figure out what it is important. That some kind of a collector that can do that at the same time. Otherwise, you're just going to lose it without recording, without having any idea what you're actually driving off. It'll drive off some things preferentially that are more volatile, obviously.
Microwave is the best way to heat the first few centimeters of regolith. So if you're hitting it with microwave, you're boiling that stuff off.
So you have a little microwave beam, and you have a little collection area cover, basically, to collect the stuff you're driving off at the same time.
And the top of your cover has to be cryogenic, so you're driving it up and catching it with little teeny pellets.
Yeah, a little cold trap.
Cold trap.
Chemists do that in the laboratory all the time. Not really easy to do on the moon, obviously, but yeah. Well, Dave?
So that cold trap, that's another heat pipe application from the microwave processing to drive it up into cold trap.
I'd really like to hear from Mohammed. Can we get him on the line now? Is he back? Did he respond to the message?
He did not respond to the message, but I'm going to unmute him. Interesting.
Okay.
Because JPL has a lot of experience in robotics. He should be on the line.
What I'm going to do is unmute him and see if we can hear him. He's got two microphones out there. Mohammed, are you listening in?
I'm listening.
Okay, I heard you. We didn't hear you in the room. Okay, say something, Mohammed. Hello? Mohammed, could you introduce yourself? Okay, I heard him a second ago, guys. I'm talking to the folks in the room. Mohammed, whatever you did, maybe you unmuted your phone or whatever, we could hear you for just a moment.
Well, I mean, I can ask the questions and maybe you can respond by text. So what I just like to get a sense of he talked about a lot of things, and I'm curious, especially in terms of the cold temperature battery and electronics applications that were talked about, what we're looking at in the way of cycling and warm-up time and efficiency, especially for the batteries when we're operating at the temperatures that we're looking at for. I mean, the JPL folks I know are trying to get down to minus 80 degrees centigrade for lithium-based batteries. So, and that'll just
Can
be
you
a
guys
start.
hear me
I have
now?
other questions. We can hear you. Yay.
Oh, okay. I think I figured out what I was doing wrong. I was both on a laptop and a desktop, and I had two channels actually listening to you at the same time. That was the echo. Okay, so the question is, what are the things in terms of cycling that we are working on at JPL? Can you repeat your question one more time, please?
Yeah. Well, also, efficiency of the electronics when you get down to those very cold temperatures. The Xilinx electronics, FPGAs.
It turns out our experience is that the FPGAs and generally electronics, they get better as you go colder. They get faster and they are really more efficient. There is a problem with life of operating electronics at very low temperatures.
And the mechanisms you were talking about, what were the temperature ranges for the mechanisms that you were talking about?
So the low temperature mechanisms that we looked at, they operated easily at temperatures of minus 240 degrees C.
Wow.
So they use what's called a dry lubricant, and the dry lubricant is a very thin film of lubricant that you put in there. It's usually made out of moly disulfide. And that allows them not to jam, and the lubricants, traditional lubricants, they freeze at certain temperatures, like oils or whatnot. And this dry lubricant doesn't freeze, going down to allowing the wheels to turn, the gears to not grind themselves at temperatures that are supporting even lunar applications.
Wow. So could you talk about, I mean, the technologies you talked about, could we be putting together systems that would include all of these cold temperature operating components now? And where do you see that? What kind of progress could we make in operation to make more compact systems with these technologies in the next 5 or 10 years?
So there's two parts. One is the electronics. The other part is the mechanism. With the electronics, the type of technologies that we would use would utilize commercial manufacturing and a different set of design rules. These design rules are process specific, and have to be empirically developed. So in case of the silicon germanium CMOS technology out of IBM that was the subject of the NASA study, we developed a set of design rules that allowed us to put together electronics that not only works at these temperatures, but works reliably for a very long time under both the condition of temperature and radiation. In terms of, go ahead, Paul.
No, I was just going to say that and they're also radiation tolerant.
That's very true.
Uh-huh.
So, if we wanted to, so the problem we have is addressing technology obsolescence. When we worked on the IBM technology at 0.5 microns, this technology right now is being considered obsolete by today's standards. This was 3 years ago, and now it's obsolete. And they're going to 50 nanometers, 45 nanometers, an order of a magnitude tighter resolution with their technologies. And so the investments that we need in delivering a electronic system that is based on custom ASICs is in terms of design and also experimental understanding of what those design rules are. So that's one comment that I have. But the physical fundamental barriers are not there. There's no barrier in us in terms of inventions that we have to think about developing that would prevent us from building an electronic system that is called capable. In terms of miniaturization, go ahead, Pam.
No, go ahead. You go ahead. Go ahead.
Okay. In terms of miniaturization, miniaturization comes with the choice of packaging. So in the presentation, I showed the work that we did at JPL developing what's called thermal cycle resistant electronics. That type of packaging uses what's called chip on board, which is considered to be a fairly advanced miniaturization technique. And because traditional chips are packaged in plastic components, the plastic packages go through glass transition temperatures and become very brittle at lunar temperatures. You cannot use them. So what you do is you eliminate the plastic and directly go and put the chip on substrates that are made either out of ceramics or temperature tolerant polymers. So that brings us to a question that I was asked via email from a colleague at Goddard with respect to FPGA, field programmable gate arrays. It's traditionally a technology that comes in a packaged part. So FPGAs are in their ceramically packaged are more temperature tolerant than commercial plastically packaged FPGAs. And then but at the end of the day, they have a finite life for operating under cycles of lunar or Martian environment. And that is less than the type of packaging recommended for chip on board that we developed at JPL. Now, in terms of mechanical systems, the fundamental limit with the mechanical systems, including sample handling and delivery, is the lubricants. The mechanical systems that are traditionally lubricated with wet lubricants are going to freeze out as a function of low temperature. Wet lubricants go and become frozen, right? So the choice of using moly disulfide or a derivative of that as a dry lubricant seems to be a successful solution going forward with building mechanical systems that could then operate in these type of temperatures. However, when it comes to putting an actuator together that works at low temperatures, there are also design rules that you consider, and those design rules compromise size. So you make the gears a little bit bigger, you make the clearances larger so that they can compensate for thermal coefficient expansions that are and mismatches between different alloys. in terms of thermal expansion and contraction, and you go from there. So did I answer your question, Pam?
Yes. Does anybody else have a question? I know we have some folks online that might like to ask a question too. Because I could just keep asking questions if nobody else has a question. Tom Riley has a question.
Just a couple of points. Molybdenum disulfide has the same crystalline structure as graphite, that is, very hard layers with a large space in between. Molecules, particularly of air and nitrogen, get between the two layers and act like ball bearings, and that's why it's such a good lubricant of this class. If you want to run it at cold temperatures, you can bake the stuff in an atmosphere of whatever molecule you like argon, and you can get better performance at the lower temperatures by simply choosing your ball bearing.
I couldn't agree any better.
Okay, sorry, Mohammed. This is Speed. John, about 9 minutes ago, said in the chat box that he would be interested in seeing a list of applications on the moon that required thermal management and that would be aided with the heat pipe technology.
Okay. I will take it as an action item to, unless we want to do it, unless we want to, I can just mention them off the top of my head. I can do more documentation in writing if that would be helpful right now, and you could take notes if you want to. Otherwise, they will be in our notes, and we do generate a white paper from the meetings. But generally speaking, we talk about most of the biggest application I can think of is a network of small stations that do environmental monitoring on the lunar surface. It's not so difficult in orbit, but on the surface, because you have to contend with the relatively long lunar night, or a network of geophysical stations that actually could potentially require mechanisms to eminence and make sure that you have a certain orientation. So actually this could be instructive for both Mohammed and John in terms of the kind of applications we could be talking about on the moon, just for starters. And we're not even talking about mobility. I'm just talking about relatively simple ones. I can kind of envision, like I talked about yesterday, a potential 12U package which had maybe 3 instruments on it that I could conceivably be pictured as a 12U system with some kind of a design that we came up with that would only have a 10% duty cycle but could survive lunar night. But the big challenge is you can come up with relatively small concepts and do limited duty cycles, but you'd really like to be able to operate all the time during lunar night, and you'd like to be able to look at 10 or 15 watts potentially, maybe a little bit more, to operate all of your instruments during lunar night. If you can come up with a heat pipe technology that could allow that operation to provide enough heat for you to then circulate the heat to keep the battery warm in an otherwise extremely cold environment, that would be great. And you could think of other kinds of applications where you have a little station on the lunar surface with several instruments that would be somewhat comparable. And the environment you would be in, it could range from equatorial to even polar environments. And as you approach the poles, you get more irregular diurnal cycles. You can get very long periods of light or very long periods of dark. So the temperature regimes are a little bit different. But nominally, we're probably thinking about something that would go from about about 50K to 400K total overall range. At the upper end of that range, if it's equatorial; at the lower end, if it's polar. Is that helpful? John?
Yes, very helpful. Thank you.
Okay. John,
I appreciate that.
Okay. And I can do more detailed, actually send you a copy of the paper I presented yesterday too. So.
Great.
And Mohammed, these are the kinds of things, if we weren't talking about mobility, which presents some special challenges or any need for special sample handling, where you have to deal with the mechanical issues, can you conceivably think of a very compact package with combining the technologies you were talking about for either the moon or Mars, a network of these small packages that could potentially be the upper end of CubeSat size?
I think that people are talking about equivalent of weather stations, that and network of seismic devices that you can put in as instruments that are standalone, and they either are talking among their peers, or they talk from short range to an orbiting satellite with some local storage, memory storage. That because when you talk to an orbiting satellite, you have to store data till you get to the line of sight, and then they start transferring data. So that's the thing that comes to my mind.
Mm-hmm. So these sort of atmosphere explorers for Mars, for example?
Yeah.
Yeah, I think it'd be a great application. Russell.
So Mohammed, I had a question for using the dry lubricants, does that scale down to like very small bearings and mechanisms? And then the other is, what is the impact of the lunar dust? Are those types of seals better or worse than the liquid types of seals?
So you asked two questions. We did not do scaling down experiments to tell you that what would be the scaled down version of the and what is the impact of scaling on dry lubricants. So I wouldn't be able to answer that. Somebody at NASA, Glenn, like Dr. Philip Abel, would be a resource that can potentially shed light into this. There are other technologies like ceramic gears that can scale down and be considered in combination with lubricant. Your other question was, can you repeat your second question? There was, sorry, I lost my train of thought.
The impact of lunar dust on dry seal bearings.
So all of the actuators that we design have a dust seal on them, and the lunar dust in particular presents a very difficult challenge because they are very sharp, these dust, and they can easily penetrate traditional dust seals that we use for Martian environments, for example. They are different kind of dust, and the lunar ones are very challenging. So the dust seals that we looked at for lunar applications are usually much more ruggedized to cover this. And then there is when you look at a motor that has a dust seal on it, the drag factor because of the dust seal is significantly larger, reducing the efficiency of the motor. It's because these dust seals wrap around the shaft of the motor and have a drag. So the lighter or the less of a seal you have, the more of a torque you have for drive, and less friction forces that you have to compensate against. So yeah, that's a good point. Dust seals are a challenge for lunar applications.
Mm-hmm. And I would assume that would be so for the high temperature superconductor related mechanisms also, for like flywheel mechanisms.
Absolutely,
yes,
for any mechanism.
Yeah.
So
well, they do, but if you so the one of the features is if you're using flywheel, if you're using superconducting bearings, you now have you can actually that was one of the original applications was a lunar telescope. So you're doing one RPM where M is a month, and you have a non-contact bearing, then the dust becomes a non-issue.
Mm-hmm.
Doing that for wheels and coming up with a non-contact superconducting bearing for a wheel is a little harder. But that's, again, another example of pushing the technology to the small scale.
Anybody else like to comment on that? I feel like I've hogged the conversation. Who else would like to make a comment or ask a question? Anybody online want to say something? We're coming down to the end. We've got about 3 minutes left. We have a question in the other part of the room.
John, do you want to say something?
I didn't hear the question. But I did have a question for Mohammed.
Go ahead.
Yeah, so my question was, if you put the various components on something like a polyimide, I was wondering how you deal with the thermal contraction for the wire, the interconnecting wires from one component to the other. That must be a challenge.
So you can look at this as a challenge or as a tool for that you may have. If you look at chip on board technology where wires are acting as the connectors, and this is not flip chip, the wires are virtually going from one chip, they get suspended in the air and go to the substrate in the other side. Their spring force acts as an asset for you. So the thermal expansion and contraction coefficient will get them to be very springy, and they're elastic. So it really doesn't present a reliability factor. What it does is, in case you have delamination from the substrate, they act as additional support, giving you a little bit longer life. In other technologies, and so this is a technology choice dependent, it may become a factor in degrading your reliability. So there are techniques that people use that allow them to add strain relief in these terminals that would minimize that factor.
Thanks.
You're welcome.
Well, thank you.